We conclude our discussion of freefall with another example of projectile motion, the name given to freefall problems in 2 dimensions. In the example worked in the last mini-lesson, we were told that the object in freefall started with a horizontal velocity. This meant that the y component of the initial velocity vector was 0, and part of the problem was to deduce the x component of the initial velocity vector. Some projectile problems, however, give you the initial speed or the initial direction of motion rather than the x or y component of the initial velocity vector. It's tempting in these situations to treat v0x and v0y as 2 unknowns, but that is misleading. In fact, if you're given either the magnitude or direction of the v0 vector, then while the specific values of v0x and v0y are not known, they are not independent. If you determine one, then you automatically get the other as well. For example, suppose you're told that the projectile has an initial speed of, say, 20 meters per second, but aren't given the initial direction of motion. The unknown is theta, the angle that the initial velocity vector makes with the horizontal. The components of the v0 vector are both related to theta by v0x equals 20 meters per second times cosine theta, and v0y equals 20 meters per second times sine theta. There is only one unknown associated with the initial velocity vector, not 2. In the example that follows, we'll see how to deal with situations like this, although for the other case in which the initial direction is given and the initial speed is unknown. A soccer player kicks the ball toward a goal that is 29.0 meters in front of him. The ball leaves his foot at an angle of 32 degrees with respect to horizontal and crosses the goal 1.50 meters above the ground. How fast was the ball going as it left the soccer player's foot? First, we draw a clear, carefully annotated picture of the situation described in the problem. After the soccer ball leaves the player's foot, it is in free fall, its motion only subject to the downward pull of gravity. The initial event of its free fall motion is when the ball leaves the player's foot, and the final event is when the ball crosses the goal. Now we can tabulate everything we can glean from the problem about the kinematic variables. As usual, we choose the origin of time and coordinates at the first event, so that t0, x0, and y0 are all 0. We're told in the problem that x sub f equals 29.0 meters and that y sub f equals 1.50 meters. Since the ball is in free fall, its acceleration is 0 in the x direction and minus g in the y direction. We're not told v0x or v0y, but we are told that the initial direction of the ball is 32 degrees above horizontal. The initial speed v0 is not given. In fact, that's what the problem asks us to compute. So we express both v0x and v0y in terms of the unknown v0 and the known angle 32 degrees. In particular, we write v0x equals v0 times cosine 32 degrees, and v0y equals v0 times sine 32 degrees. We know that whatever v0x is, v sub fx is the same, since there's no horizontal acceleration. We're not told anything about t sub f or v sub fy. So the unknowns in this problem are v0, the initial speed of the ball, t sub f, the final time, and v sub fy, the y component of the final velocity. We're now ready to start solving for the unknowns. For convenience, we'll start out by focusing on v0 and t sub f, and we'll worry about v sub fy later. It turns out that we can't find a single equation in which the only unknown is either v0 or t sub f. So we'll have to find 2 equations containing these 2 unknowns. We start with the first constant acceleration equation for the x motion. Since t0, x0, and most importantly a sub x are all 0, this equation simplifies to x sub f equals v naught cosine 32 degrees times t sub f. And since we know the value of x sub f, this equation only has v naught and t sub f as unknowns. Next, we write down the first constant acceleration equation for the y motion. Here, only t naught and y naught vanish, so we're left with y sub f equals v naught sine 32 degrees times t sub f minus 1/2 g t sub f squared. And again, since we know y sub f and g, this equation only has v naught and t sub f as unknowns. We now have two equations in two unknowns, exactly what we need to solve for both. Let's solve the first equation for t sub f and then insert that into the second equation. Notice that in the first term, v naught appears in both the numerator and the denominator, and thus cancels. This leaves v naught isolated in the second term. This is kind of an ugly equation, and it would be perfectly reasonable to insert numbers at this point to tidy it up a bit. But just for fun, I'm going to leave it in terms of symbols and insert numbers only at the very end. And here's the expression that results. After inserting numbers and evaluating, we find that the initial speed is 18.6 meters per second. Now that we know v naught, we can plug it back in to find t sub f, which turns out to be 1.84 seconds. And we can find v sub fy using the second constant acceleration equation for the y motion. All the variables on the right-hand side are now known, so we can just plug in numbers and evaluate to find that v sub fy is minus 8.21 meters per second. We can now update our table of kinematic variables to fill in the previously unknown values. And finally, we're ready to answer the question in the problem. How fast was the ball going as it left the soccer player's foot? Well, that's just v naught, which we computed earlier to be 18.6 seconds. Note that we didn't really need to calculate t sub f and v sub fy in this problem after we found v naught, since the problem only asked for v naught. We just did it for fun and to get some extra practice.